Your heating system is going to fail. Not might fail, going to fail. And when it does, probably during the coldest night of the year, you'll have approximately 8 hours before your house drops below 50 degrees Fahrenheit and your family start experiencing the early stages of hypothermia. Most people think they are prepared because they have a generator or a fireplace or a stack of blankets. And all of those people are wrong. Because generators run out of fuel in 12 to 18 hours and cannot be refilled during ice storms when gas stations have no power. Because fireplaces without external air intake create negative pressure that sucks cold air through every crack in your house while sending 80% of heat up the chimney. Because blankets are insulation, not heat sources, and they only slow heat loss from a body that is already producing inadequate warmth in a freezing environment. I know this because I just spent 48 hours proving it. I deliberately cut power to my house during a winter cold snap, with outside temperatures dropping to 15 degrees Fahrenheit at night. No electricity, no furnace, no space heaters, no generator, just one room, basic physics, and a method so simple that explaining it sounds ridiculous until you understand why it works. Drop heat in the comments if you trust your current heating backup plan. Drop cold if you are realizing you have a vulnerability you have not addressed. Because what I am about to show you is the difference between confident survival and desperate suffering when the grid goes down during winter. And before you dismiss this as unnecessary or extreme, understand that power outages during winter are increasing every year. Texas froze for a week in February 2021. For a million people without power, some for 10 days, dozens dead from hypothermia in their own homes. Pacific Northwest ice storm, December 2022, 500,000 without power for a week. Midwest polar vortex, January 2024, wind chills at -50. Rolling blackouts lasted 72 hours. This is not hypothetical. This is recurrent reality. And your heating system depends on electricity, even if you have natural gas or propane. The ignition system is electric. The blower is electric. The thermostat is electric. No power means no heat regardless of fuel source. Let me explain what happened during my 48-hour test. Day 1, 6 a.m., outside temperature 22 degrees. I shut off the main breaker. House temperature was 68 degrees. I had prepared one room, using the method I am about to teach you. By 6 p.m., 12 hours later, outside temperature had dropped to 18 degrees, and the rest of my house was down to 52 degrees. The prepared room was holding at 63 degrees. By midnight, outside at 15 degrees, the rest of the house was 48 degrees. The prepared room was 61 degrees. Day 2, 6 a.m., outside climbed back to 20 degrees. Unprepared house areas were 46 degrees. Prepared room was 59 degrees. By day 2 at 6 p.m., 48 hours into the test, outside was 19 degrees. Unprepared house was 45 degrees, and the prepared room was still at 58 degrees. I spent those 48 hours sleeping, working, and living comfortably in that one room, while the rest of my house became uninhabitable. And the method that made this possible costs approximately $200 to implement and requires no ongoing fuel source. The one-room trick is not a trick. It is applied thermodynamics. You are going to isolate the smallest livable space in your home, seal it thermally from the rest of the structure, implement passive insulation barriers, create thermal mass for heat storage, introduce a minimal manual heat source, and manage the 3 variables that determine whether you maintain survivable temperature or succumb to cold. Those 3 variables are heat generation, heat retention, and moisture management. Get all 3 right, and you can maintain 55 to 65 degrees in one room, while outside temperature is in the teens and the rest of your house freezes. Get any one wrong and you fail. Let me show you exactly how this works. Step 1 is room selection. You need the smallest room in your house that can realistically contain your family for extended periods. A bedroom works. A large bathroom works if you have space for sleeping. A den or office works. The critical factor is volume. Heat capacity is measured in BTUs, British thermal units, which is the energy required to raise 1 pound of water 1 degree Fahrenheit. Air has thermal capacity of approximately 0.024 BTU per cubic foot per degree. That means heating a 10 by 10 room with 8-foot ceilings, 800 cubic feet, by 10 degrees requires 192 BTUs. Heating a 20 by 20 room with the same ceiling height, 3,200 cubic feet, requires 768 BTUs for the same temperature increase. 4 times the volume requires 4 times the heat energy. This is why you cannot heat your entire house with candles or body heat or minimal sources. But you can heat one room. During my test, I used a 12 by 14 bedroom, approximately 1,300 cubic feet. This housed 2 people comfortably with sleeping space, a small work area, stored water, food, and entertainment. It was large enough to prevent cabin fever, but small enough to heat with minimal energy input. The room had 1 exterior wall with 2 windows and 3 interior walls with 1 door. This is important because exterior walls lose heat faster than interior walls. You want to minimize exterior wall surface area while maximizing interior walls that share heat with the thermal mass of the rest of your house, even though you are not heating it. Step 2 is sealing. You need to create a thermal barrier between your survival room and the rest of the house. Most people think this means closing the door. Closing the door helps. It is not sufficient. A standard interior door has gaps at the top, bottom, and sides totaling approximately 1 to 2 inches of cumulative opening. That gap allows air exchange that equalizes temperature between your room and the cold house. You need to seal it. I use foam weather stripping on the door frame, a door sweep on the bottom, and a rolled towel as backup draft blocker. This reduced air exchange by approximately 90%. I also sealed heating vents with plastic sheeting and tape. If your forced air system is not running, vents become cold air pathways from basement or attic spaces. Seal them completely. Windows are your biggest heat loss mechanism. A single-pane window loses heat at a rate of approximately 1 BTU per square foot per hour per degree of temperature difference. Double-pane windows cut that roughly in half. But even double-pane windows in a 10-degree temperature differential, which is what you're trying to maintain, are bleeding heat constantly. You need to add insulation. I use emergency reflective blankets, the cheap foil-backed mylar sheets, taped directly to the window glass. This creates a radiant barrier that reflects infrared heat back into the room while adding a thin insulation layer. Then I hung a heavy blanket over the reflective barrier, creating an air gap between layers. Air is an excellent insulator when it is trapped and still. The blanket plus reflective barrier system reduced window heat loss by approximately 70% compared to bare glass. This is critical. Without window insulation, you cannot maintain temperature in any room regardless of heat input. Step 3 is thermal mass. This is what most survival advice completely misses. Thermal mass is material that absorbs heat energy and releases it slowly over time. Water is the best thermal mass available to civilians. Water has a thermal capacity of 1 BTU per pound per degree, which is 40 times higher than air. This means 1 gallon of water, 8.3 pounds, can store 83 BTUs per degree of temperature increase. If you heat that gallon from 60 to 80 degrees, you have stored 1,660 BTUs in 8 pounds of material. That stored energy radiates slowly back into the room as temperature drops, moderating temperature swings and extending the time between active heating sessions. During my tests, I placed 30 gallons of water in the room in various containers. 5-gallon buckets with lids, 1-gallon jugs, 2-liter bottles, distributed around the perimeter, not clustered. This provided approximately 250 pounds of thermal mass that absorbed heat during active heating periods and released it during rest periods. The effect was dramatic. Without thermal mass, room temperature would spike during heating and crash between sessions. With thermal mass, temperature remained within a 5-degree band. This is the difference between comfortable habitation and constant cycling between too hot and too cold. You can also use other thermal mass. Bricks work. Concrete blocks work. Sand-filled containers work. But water is superior because of high thermal capacity per pound, and because stored water serves a secondary purpose of providing drinking water if your pipes freeze. I rotated through the stored water during the test, ensuring both thermal mass function and hydration. Multiple purposes from a single resource. This is efficiency. Step 4 is the heat source. This is where people make catastrophic mistakes. They try to use propane heaters indoors, which creates carbon monoxide poisoning risk and consumes oxygen. They use kerosene heaters, which create toxic fumes and moisture. They burn charcoal, which produces lethal carbon monoxide. They use candles, which provide almost no meaningful heat. The correct answer for supplemental heating in a sealed room is a catalytic heater designed for indoor use or a clean-burning alcohol source. During my test, I use a single-burner alcohol stove with denatured alcohol fuel, not isopropyl alcohol. Denatured alcohol. The distinction matters. Denatured alcohol burns clean, producing primarily carbon dioxide and water vapor with minimal other combustion products. It does not produce significant carbon monoxide if burned in a well-designed burner. It is available at hardware stores, and it produces approximately 9,000 BTUs per pint burned. I burn approximately 1 pint every 4 hours during active heating sessions, providing roughly 2,000 BTUs per hour for 30 minutes, then allowing the room to coast on stored thermal mass for 3.5 hours. This pattern maintained temperature in the target range, while consuming only 12 pints of fuel over 48 hours. $12 worth of fuel kept the room habitable for 2 days. Here is why this works when other methods fail. The alcohol burner is heating the thermal mass, not the air directly. I placed the burner near the water containers during burning sessions. The water absorbed the heat energy. The water then radiated that energy over hours. This is indirect heating that creates stable temperature rather than rapid swings. It is the same principle that makes radiant floor heating comfortable while forced air heating feels uneven. Thermal mass moderates and stabilizes. But heating creates a secondary problem that kills people even when they successfully maintain temperature. Which brings us to step 5, and this is critical: moisture and oxygen management. When you seal a room, you create 2 immediate risks: carbon dioxide buildup from respiration and combustion, and humidity buildup from respiration, combustion, and any moisture sources. Both will kill you if not managed. Carbon dioxide is not directly toxic at concentrations below 5%, but as CO2 increases, oxygen percentage decreases. Normal air is 21% oxygen. Below 19.5% oxygen, you start experiencing hypoxia symptoms: headache, dizziness, impaired judgment. Below 17%, you have rapid mental deterioration. Below 15%, you lose consciousness. A sealed room with 2 people will drop from 21% to 19% oxygen in approximately 8 to 12 hours, depending on room size and activity level. You need air exchange, not continuous. Periodic. During my test, I opened the door fully for 5 minutes every 4 hours. This provided complete air exchange with the rest of the house, which was cold but oxygen-rich. 5 minutes was enough to equalize gases without significantly dropping room temperature, because air has low thermal capacity. The walls, floor, ceiling, and thermal mass retained heat and quickly rewarmed the fresh air. This 5-minute exchange every 4 hours maintained oxygen above 20% throughout the test. Simple, effective, necessary. Moisture is more insidious. Humans exhale approximately 1 cup of water vapor per person per day through respiration, more during activity. Combustion produces water vapor. If you are heating water for drinks or food, you add steam. In a sealed room, relative humidity climbs rapidly. Above 60% relative humidity, you start developing condensation on cold surfaces like windows and exterior walls. Above 70%, you risk mold growth. Above 80%, condensation becomes significant, and you start feeling clammy and cold even at reasonable temperatures because evaporation from your skin is inhibited. High humidity makes you feel colder than dry air at the same temperature. This is counterintuitive, but critical. Humidity above 60% means any air movement or temperature drop causes moisture to condense on your skin, and evaporation cools you. You end up feeling cold even in a heated room. The solution is moisture control through ventilation and absorption. During my test, I monitored humidity with a cheap hygrometer. When humidity climbed above 60%, I increased ventilation frequency or duration. I also kept a bucket of desiccant, specifically damp rid calcium chloride, which passively absorbs atmospheric moisture. The combination kept humidity between 45 and 55% throughout the test. Comfortable and safe. Pause here. We have covered the 5 core components of the one-room survival method. Room selection for minimal volume. Sealing to prevent heat loss. Thermal mass to stabilize temperature. Clean heat source for energy input. Ventilation for oxygen and moisture management. Total cost to implement all 5 is approximately $200. Foam weather stripping, $20. Reflective blankets and hanging blankets, $40. Water containers, $30 if you buy new. Free if you repurpose. Alcohol stove and fuel for 1 week, $50. Hygrometer and desiccant, $30. Miscellaneous supplies like tape and tools, $30. $200 provides a capability to survive indefinitely without electrical heating. Most people will quit watching right here because they want a magic solution, a single product, a simple answer. If you are still here, comment "still here" right now. Because what comes next is the hour-by-hour reality of living this method, and the problems I encounter that textbook physics does not warn you about. Hour 6, midnight of day 1. Room temperature had been holding steady at 62 degrees. Outside was 15 degrees. I went to sleep. By hour 12, 6 a.m. day 2, I woke up and room temperature had dropped to 59 degrees. Not catastrophic, but below my target minimum of 60 degrees. Why? Because during sleep, I was not moving and my body heat production dropped. Basal metabolic rate produces approximately 60 to 80 BTUs per hour. Active metabolism produces 2 to 4 times that. While sleeping, I was producing minimal heat and the alcohol burner had been off for 4 hours. The thermal mass was radiating its stored energy, but the room was still losing heat to the exterior faster than thermal mass could compensate. The solution was increasing thermal mass and extending burn time slightly. I added 10 more gallons of water and changed my heating schedule to 30 minutes of burning every 3 hours instead of every 4 hours. This provided more frequent energy input and more thermal storage capacity. By hour 18, the room had stabilized at 61 degrees even during sleep periods. The lesson here is that theoretical calculations are starting points. Real-world testing reveals adjustments. You need to practice this method before you depend on it in crisis. Adjust thermal mass. Adjust heating frequency. Adjust ventilation. Find what works for your specific room in your specific climate. Hour 24, noon of day 2. I was working on a laptop, which was running on a portable power station, not part of the no electricity test, since the point was proving heating is viable. The laptop was generating approximately 20 to 30 watts of heat, roughly 70 to 100 BTUs per hour. Not significant for room heating, but not zero either. What I noticed was that active work, typing, moving around, kept me comfortable even as room temperature drifted down to 60 degrees. When I stopped working and sat still, I felt cold at the same temperature. This is metabolic heat production again. Activity produces heat. Stillness does not. During actual power outage survival, you should plan activities that keep people moving during waking hours. Exercises, household tasks, games that involve movement. This reduces the heating burden and makes lower temperatures tolerable. Hour 36, midnight of day 2. This is where psychological factors became apparent. The room was objectively comfortable at 61 degrees. I was warm enough under one blanket, but the isolation was mentally wearing. Spending 36 hours in a 12 by 14 room with minimal entertainment, no internet because I deliberately cut power, limited books and activities, creates cabin fever. I found myself opening the door just to look at the rest of the cold house, to see different walls, to walk around. This is not a physical survival problem. This is a psychological endurance problem. And it matters because if you cannot mentally tolerate confined space for extended periods, you will make bad decisions like leaving the survival room to go to another part of the house where temperature is unsafe. The solution is preparation before crisis. Stock the survival room with books, games, activities, entertainment that does not require electricity, cards, board games, books you've been meaning to read, puzzles, craft projects, things that occupy hands and mind. Also, If you have family or group, social interaction prevents isolation psychology. You talk, you play games together, you create entertainment. Solo survival is psychologically harder than group survival, even in identical physical conditions. Plan for this. Recognize that boredom and isolation are threats to decision-making quality. Hour 42, 6 a.m. of day 3, approaching test completion. Room temperature was holding at 59 to 62 degrees, depending on heating cycle phase. I had consumed 12 pints of alcohol fuel at $1 per pint. I had managed moisture and oxygen successfully with no condensation problems and no symptoms of poor air quality. I had slept comfortably using 2 blankets instead of my normal one. I had maintained work capability and mental clarity. The test was validating the method, but I also identified improvements. More thermal mass would further stabilize temperature. Better window insulation, possibly rigid foam boards instead of blankets, would reduce heat loss. A slightly larger room would improve psychological tolerance without dramatically increasing heating requirements. What I am about to say will anger the commercial preparedness industry and the people selling expensive generators and propane heaters. If you are ready for uncomfortable economic truth they actively suppress, hit the like button right now. Here it is. You do not need thousands of dollars of equipment to survive winter power outages. You need to understand thermodynamics and implement basic physics principles with minimal cost. The preparedness industry sells fear and complexity because they cannot make money on simple solutions. A $200 investment in insulation, thermal mass, and clean fuel provides equal or superior heating security compared to a $2,000 generator that runs for 12 hours then becomes useless when fuel is gone. Generators have value. I own one. But generators are not primary heating solutions for extended outages. They are temporary bridges for short disruptions. For multi-day or multi-week outages, passive thermal management beats active heating every time because passive systems do not depend on fuel resupply. Once you set up the one-room method, it functions indefinitely as long as you have minimal fuel for supplemental heating, and that fuel can be stockpiled cheaply. 50 pints of denatured alcohol, enough for approximately 2 weeks of heating at my test consumption rate, costs $50 and stores in a 1 cubic foot space. Compare that to 50 gallons of gasoline for a generator, which costs $200, requires proper storage containers, degrades over 6 to 12 months, and presents fire and explosion hazards. The physics is undeniable. Small sealed spaces with thermal mass can be maintained at survivable temperatures using minimal energy input. This is not theory. This is my lived experience over 48 hours with measured data. Room temperature never dropped below 58 degrees despite outside temperature hitting 15 degrees. I never experienced discomfort beyond initial adjustment to sleeping in a cooler room than I normally prefer. I maintain work capability, sleep quality, and decision-making clarity. The method works. Let me address implementation questions I know you are thinking. What about carbon monoxide? Denatured alcohol burned in a proper stove produces minimal carbon monoxide, but you should have a battery-operated carbon monoxide detector in the room as fail-safe. They cost $20 and run for years on batteries. Test it monthly. Replace batteries annually. Never compromise on this. Carbon monoxide is odorless and lethal. What about children? This method works for families. Larger rooms require proportionally more thermal mass and slightly more fuel, but the principles scale. A 20 by 20 room would need perhaps 60 gallons of water thermal mass and 1 pint of alcohol every 3 hours instead of every 4. Still manageable and affordable. What about pets? Pets produce body heat and consume oxygen. Factor them into air exchange scheduling. Otherwise, they benefit from the same warm room you do. What about cooking? The alcohol stove that heats the room can also heat water and cook simple foods. You boil water for coffee, tea, or dehydrated meals. You heat canned soup. You are not preparing gourmet meals, but you can meet nutritional needs. What about sanitation? If your bathroom is not the survival room, you need a backup plan. 5-gallon bucket with a toilet seat lid and heavy-duty bags serves as emergency toilet. Sawdust or cat litter controls odor. Not pleasant but functional. What about water if pipes freeze. This is why the thermal mass water serves double duty. 30 gallons provides drinking and hygiene water for a family for a week. You can melt snow if necessary. You can collect ice and let it melt in the warm room. Hour 48. 6 p.m. of day 3. I turned the main breaker back on. Test complete. The rest of the house was 44 degrees. Walking into those rooms felt shockingly cold after 48 hours of acclimation to 60-degree comfort. The furnace took approximately 4 hours to bring the house back to normal temperature. During that time, I compiled data and reflected on lessons learned. The primary lesson is that comfort is relative and adaptable. 60 degrees felt cold for the first 6 hours. By hour 12, it felt normal. By hour 24, it felt comfortable. Your perception of cold is partly physiological and partly psychological. You can adapt to lower temperatures faster than you think if the temperature is stable and you are not losing body heat to drafts or cold surfaces. The secondary lesson is that preparedness is not about having the perfect plan. It is about having a viable plan and the willingness to adapt when reality differs from theory. My initial heating schedule was insufficient. I adjusted. My initial thermal mass was inadequate. I added more. These adjustments happened during the test because I was monitoring and thinking critically rather than rigidly following a predetermined protocol. Survival is dynamic. You observe, you assess, you adapt. The people who survive are not the ones with the perfect plans. They are the ones who can modify plans when conditions change. Real talk. How many of you have never tested your emergency heating plan? How many of you have a plan that exists only in your head or on paper, but has never been validated under real conditions? Drop a flame emoji in comments if this describes you. You are not alone. Most people do not test because testing is uncomfortable and requires effort. But untested plans are fantasies. Tested plans are capabilities. The difference is everything when crisis hits. Here is your action plan. This weekend, implement a 4-hour test. Pick your survival room. Seal it using the methods I described. Set up thermal mass. Turn off your furnace. See what happens. 4 hours is not 48 hours, but it is enough to identify problems and validate basics. Do you have adequate window insulation? Is your door seal effective? Does temperature drop faster than expected? 4 hours reveals these issues while maintaining safety because you can abort and turn heating back on if something goes wrong. Then you adjust and test again. Work up to 8 hours. Then 12. Build confidence through progressive testing rather than hoping your theoretical plan works when you desperately need it. The one-room trick is not a trick. It is physics applied correctly. Heat generation through clean fuel. Heat retention through insulation and sealing. Heat stabilization through thermal mass. Oxygen and moisture management through periodic ventilation. These 4 principles, implemented in the smallest practical space, provide indefinite heating security without dependence on grid power or complex equipment. The principles are scalable from single rooms to small houses if you adjust quantities proportionally. The principles work regardless of climate if you understand that colder climates require more insulation and more thermal mass, but the method remains fundamentally the same. You now know more about practical cold weather survival without electricity than 99% of preppers who bought expensive gear without understanding basic thermodynamics. That is your advantage. Most people will suffer through power outages because they never learned these principles. You will not because you now have the knowledge. Knowledge without application is trivia. Knowledge with application is survival capability. The question is which one you choose. Let me synthesize this into a checklist you can reference. Room selection, smallest viable space, preferably one exterior wall, multiple interior walls for thermal coupling to the rest of the house. Ceiling, weather strip door frame, door sweep, rolled towel draft blocker. Seal heating vents with plastic and tape. Window insulation, reflective emergency blankets taped to glass. Heavy blankets hung with air gap over reflective layer. Thermal mass, minimum 30 gallons of water in distributed containers. More is better up to practical limits of space. Heat source, alcohol stove with denatured alcohol fuel. 1 pint per 3 to 4 hours of heating. Stored quantity based on expected outage duration. Ventilation protocol. Open door fully for 5 minutes every 3 to 4 hours to exchange air and manage oxygen and moisture. Monitoring equipment. Thermometer to track temperature, hygrometer to track humidity, carbon monoxide detector as safety backup. Supplies, desiccant for moisture control, stored water for drinking, emergency toilet setup, food that requires minimal preparation, activities for psychological endurance. This complete system costs approximately $200 to $300, depending on what you already own and what you need to purchase. Compare that to alternatives. A propane heater rated for indoor use costs $150 to $300. Propane fuel at winter heating rates consumes approximately 1 to 2 pounds per hour, which is $2 to $4 per hour at current propane prices. 48 hours of heating costs $100 to $200 in fuel alone. A generator capable of running a furnace costs $800 to $1,500. Gasoline at winter heating rates consumes approximately half a gallon per hour, which is $2 to $3 per hour. 48 hours costs $100 to $150 in fuel. And both options require fuel resupply, create noise and exhaust problems, and have mechanical failure points. The one-room method costs $200 setup, $12 for 48 hours of fuel, scales indefinitely with stockpiled fuel, has no mechanical parts to fail, and operates silently. The economics are overwhelming, but the strongest argument is not economic. The strongest argument is reliability. Generators fail. Propane heaters malfunction. Complex systems break under Murphy's Law, which states that anything that can go wrong will go wrong at the worst possible time. Simple systems work. Sealing a room does not fail. Thermal mass does not break. Alcohol fuel does not degrade rapidly. Ventilation protocol does not have mechanical parts. The one-room method is anti-fragile, meaning it is resistant to cascading failures that destroy complex systems during crisis. You set it up correctly once, and it functions every time you need it with minimal maintenance. I want to address the elephant in the room. Some of you are thinking this sounds like too much work, that buying a generator or heater is easier. And you are right. It is easier until it is not, until the generator will not start, until propane supplies are sold out, until you run out of fuel with days of outage remaining. Easy during normal times becomes catastrophic during crisis. Difficult during normal times becomes life-saving during crisis. The one-room method requires effort to set up and test. That effort buys you independence from supply chains, from mechanical reliability, from fuel availability. That is the value proposition. Effort now, purchases security later. Let me tell you what I learned about myself during those 48 hours. I learned that comfort is a mindset more than a condition. I learned that boredom is a more immediate threat than cold when temperature is stable. I learned that psychological preparation matters as much as physical preparation. I learned that I can adapt to conditions I would have previously considered unacceptable. These are valuable lessons that you cannot learn by reading or theorizing. You learn them by doing, by testing, by experiencing controlled discomfort in safe conditions, so that uncontrolled discomfort in dangerous conditions does not break you. This is why I encourage you to test this method, even if you have backup heating, even if you have a generator and propane heater and fireplace. Because learning that you can maintain warmth with minimal resources builds psychological resilience that transcends a specific scenario. You prove to yourself that you are not dependent on complex systems, that you can problem solve under constraints, that you have capability beyond what you thought possible. That confidence changes how you approach all preparedness challenges. Honest question: what is the one component of this method you are implementing this week? The room sealing? The thermal mass setup? The alcohol stove testing? Comment below. I read every single one. And if you think I am wrong about generators being inferior for extended outages, good. Drop your reasoning. Best comment gets pinned and a detailed response. Because I want you thinking critically, not accepting my conclusions blindly. Test. Verify. Form your own conclusions based on experience. If this video changed how you think about winter preparedness, share it with one person who lives in a cold climate. Not for me, for them. Because they deserve to know that surviving winter power outages does not require thousands of dollars of equipment. They deserve to know that physics and preparation beat expensive gear and hope. Stay warm, stay prepared, or stay dependent on systems that fail when you need them most. Your choice. But understand that the choice you make determines outcomes for yourself and the people depending on you. I made my choice. I tested the method. I documented the results. Now you have the information to make your choice. One more thing. See that progress bar? Not quite done yet. 99% leave before this final section. The 1% who stay get the mistake I made that almost ruined the test and the solution that saved it. Comment thermal if you are still here. Welcome to the 1%. The mistake was initial ventilation timing. I started with 5-minute air exchanges every 6 hours because I wanted to minimize heat loss. By hour 20, I had a severe headache and could not focus. I checked the carbon monoxide detector, which showed safe levels. I checked the thermometer, which showed 61 degrees. Then I checked the hygrometer and realized humidity had climbed to 78%. High humidity was inhibiting evaporative cooling from my skin, making me feel simultaneously clammy and oxygen-deprived, even though oxygen levels were technically adequate. The moment I opened the door and let dry air flow in for 10 minutes, symptoms disappeared. The lesson? Trust your body. When something feels wrong, investigate methodically. Do not ignore symptoms. They are data. That mid-test correction taught me more than any amount of research could have. Practical experience reveals problems that theory misses. Test your systems. Learn from problems. Adapt. That is how you build real survival capability.